This is Unit 4, Investigation 3, Lessons 3 and 4. We're going to start off with the entry ticket together, just as a little refresher on factoring. We always want to multiply to the last term and add to the middle term. So here we can first take out 2x squared, because every single one of these terms can be multiplied, it can be divided by. First, we're going to start off with factoring out 2x to the second, because every single one of these terms can be divided by 2x to the second. If we do that, we are left with x to the second, because 2x to the second times x to the second gives us 2x to the fourth. Here we're left with 5x, because 5 times 2 is 10. X times x to the second is x to the third. And then we're left with plus 6, because 6 times 2 is 12, and we already have that x to the second. Then we got to factor this polynomial in the parentheses. So here, the same thing, we got to add to the middle term, multiply to the last. So I will be left with plus 3 plus 2, because 3 times 2 is 6, and 3 plus 2 is 5. And I'm still left with this 2x to the second on the outside. Here, we can factor out 3, but we can also factor out an x. So 3x, I'm going to be left with x plus 4x. Oh, this is x to the second. So x to the second plus 4x minus 12. So from here, I can actually factor out 6 times negative 2 is negative 12, and 6 plus a negative 2 is 4. And I still have this 3x on the outside. And we have our full factorizations. We're going to be using the same idea to practice factoring by substitution. Here I'm going to change the equations on you a little bit, just because there was a couple typos on the top over there. But if we can factor out a 4x, so 4x to the second, if I square that, 4 to the second is 16, x to the second is x squared, so we get that 16x squared. Here, if we have 8 times 4, that gives us 32, and then we have that x left over, and then we have our plus 15. So we have not changed this expression just yet. Now we're going to do the z substitution. So we're going to factor by substitution. I'm going to use the letter z. So I'm going to say let z equal 4x. So now instead of 4x, I'm going to write z. So I'm going to have z squared plus 8z plus 15. And this is a lot easier for me to factor, because I can actually factor this pretty easily. I need to factor so it multiplies to 15 and adds to 8. Well, 5 times 3 is 15, and 5 plus 3 is 8. So I have my factorization. Now I got to resubstitute in this 4x for z. So I'm going to have 4x plus 5 times 4x plus 3. And this should be the full factorization. If we were to do this one, we have x to the 10th plus 10x to the 5th plus 21. If we take x to the 5th and square it, we get x to the 10th. If we take 10 and multiply by x to the 5th, we get 10x to the 5th. So again, we haven't changed this problem at all. We're just going to substitute x to the 5th in for z. So we're going to say let z equal x to the 5th. And now I can factor if I do that, because I have x squared plus 10z plus 21. So if I let z be equal to x to the 5th, so let z equal x to the 5th, I'm going to get x. Let z be equal to x to the 5th. I'm going to get z squared plus 10z plus 21. So again, I just put z in place of x to the 5th. Now I can factor really easily, because I need to make sure that I'm multiplying to 21 but adding to 10. Well, I actually only have one option here. plus 7 plus 3. 7 times 7 times 3 is 21. 7 plus 3 is 10. Then we're going to substitute our x to the 5th back in. So I'm left with x to the 5th plus 7, x to the 5th plus 3. Lastly, I have 49x to the 2nd plus 35x plus 6. I'm going to let z equal 7x. So I have 7x squared because 7 squared is 49. X squared is x squared. So we have 49x squared. Then we have 7x times 5. 7 times 5 is 35. Then you have that x left over. And then you have your plus 6. So nothing, again, has changed. I'm just going to substitute z in for 7x. So I have z squared plus 5z plus 6. So if I have to factor this, I'm factoring it with plus 3 plus 2. 3 times 2 is 6, and 3 plus 2 is 5. Then I can substitute back in my z value. So I have 7x plus 3 times 7x plus 2. And those are my factorizations. On the next page, we're going to be introduced to factoring by grouping. So not every single term might share a common factor, but there's pairs of terms that might share a common factor, which means like there might be two terms that share a factor, and you can factor it out of those two terms, but not the other terms in the polynomial. So we're going to do an example. And if we look at this polynomial here, x to the 3rd plus 3x to the 2nd minus x minus 3, there are no common factors between every single term, so we could do factoring by grouping. So if we look at these first two terms, we know we could factor out an x squared out of both of those terms. And if we distribute back in, we get x squared times x gives us that x third. X squared times 3 gives me that 3x squared. Now, if you look in the green, we can, on the last two terms in this polynomial, we can factor out a negative 1. So underline a negative 1 in green, and we can factor that out to get x plus 3. And if you distribute back in, negative 1 times x gives us that negative x, and negative 1 times 3 gives us that negative 3. So we haven't changed the problem at all. We have not changed the expression whatsoever. But our first step was to factor out that x squared and negative 1 from each pair of terms. Then, if we notice the same thing underlined in yellow, we have x plus 3, x plus 3. So when we factored that x squared and negative 1 out of each pair, we got left with x plus 3 twice on both ends, right? So in this situation, we can actually factor out the x plus 3 because both pairs contain it. So we're factoring out the x plus 3. So when we do that, we're going to be left with the remaining terms that are on the outside of those parentheses. So if we're going to factor out that x plus 3, well, we're going to be left with x squared minus 1. And this makes sense because if you distribute back in, x plus 3 times x squared is going to give you x times x plus 3. And then x plus 3 times negative 1 is just going to give you this negative 1 times x plus 3. So it doesn't matter how you write it. It's still going to be equivalent. So we factored out that x plus 3. Now we got to factor it out even more. So we have to factor out that x squared minus 1 because we can factor that further. We know that if we have a x plus 1 and x minus 1 and we're multiplying them together, that we're going to get x squared minus 1. Negative 1 times 1 is a negative 1, and then the middle terms will cancel if you multiply these out. Okay? So overall, even though we made a couple different changes, this last expression is the factorized form of this polynomial. We're going to be using the same method to do grouping by factoring. We're going to do factoring by grouping on these next couple examples. So this first example, I'm looking at these first two terms. So I'm going to use green. And I know I can factor out an x squared. So if I factor out an x squared, I'm going to be left with x plus 7. Now I'm going to go to my second two terms, and they don't share any variables, but they do share a number. They could both be factored out by 4. So if I have negative 4, then I'm going to be left with x plus 7 in this parenthesis as well. Because if you multiply that in, negative 4 times x is negative 4x. Negative 4 times 7 is negative 28. Be careful with your signs. Now, because I factored that out, I can see that I have x plus 7 in common. So I can factor that out of both of those terms. So I have x plus 7, and I'm left with x squared minus 4. And in this situation, I actually can factor this further because x squared minus 4 is equal to x plus 2 times x minus 2. So if I were to write this complete factorization, I would have x plus 7 times x plus 2 times x minus 2. I'm going to do the same process again for B. So starting off with green, my first two terms, I can factor out an x squared. So if I factor an x squared out, then I'm going to be left with x plus 2. X squared times x will give me that x to the third. X squared times 2 gives me that 2x to the second. Then in blue, I'm going to factor out a 7. 7 times x will give me that 7x. 7 times 2 will give me that 14. So I have x plus 2 that both of them share. So I can factor out x plus 2. And I'm left with x squared plus 7, which I cannot further factor. And that is my complete factorized form. Lastly, we have, again, we're going to start with green. We can factor out x squared from here. So x squared times x will give me that x to the third. X squared times 2 will give me that 2x squared. Now I'm going to change back to blue. I can factor out a 4. So in parentheses, I'm going to have x plus 2. And again, we're going to see that we have x plus 2 in common. So we can factor x plus 2 out. And we're going to be left with x squared plus 4, which we cannot factor further. All right. And notice that when we have the yellow parts, when I highlight in yellow and I'm highlighting the factor they both have in common, that you'll know if you're doing something wrong or if something's not adding up, if you're factoring by grouping and not both of those factors line up immediately. Okay. Moving on to lesson 4, we're going to be looking at the concept development. We're going to be discovering a new identity, but we're going to come back to this chessboard legend in a second. First, we're going to do some examples. So here they're asking you to multiply in an x minus 1 into each of these polynomials and to distribute to get a simplified expression. So here I did all the distributing for you. So now we have to simplify together. So here after we distribute, we know our x and negative x will neutralize to 0. So I'm going to be left with x squared minus 1 here. In this second example, I'm going to have x squared and negative x squared, x and negative x neutralize. So I'm going to be left with x to the third minus 1. In number 3, I distributed. Now I have to simplify. X to the third and negative x to the third will neutralize. X to the second and negative x to the second neutralize. And x and negative x neutralize. So here I got x to the fourth minus 1. Lastly, number 4, I distributed. Then I see that x to the fourth and negative x to the fourth will neutralize. X to the third and negative x to the third will create 0. It'll neutralize, right? X to the second and negative x to the second are also going to neutralize to 0. And x and negative x will neutralize to 0. So here I'm left with x to the fifth minus 1. So if you're kind of already noticing some sort of pattern here, you can kind of see that, okay, well, if if these terms in purple are my leading terms, and that's what I'm multiplying x minus 1 against, I see that I have an x value that's 1 power larger than I started with when I'm multiplying by x minus 1, which does make sense because if you have x to the third and you're multiplying by x, you obviously will get an x to the fourth, right? Because you're multiplying by another x and so on. So it does make sense, but you'll see that the middle terms will all cancel out, right? They'll neutralize to 0, and then you're left with just a minus 1 at the end. So here they ask us, okay, well, based on that pattern that we just noticed, what will the answer to this problem be without having to do all that work out? Well, I can assume that this is going to be, because we're multiplying by x minus 1 again, that this is going to be x to the 10th minus 1. So basically a general rule of thumb, they're asking us for a general algebraic identity, we're going to have an answer of, okay, well, x to the n plus 1, so whatever power n that there is in that polynomial, we're adding 1, and then we're subtracting 1 from that entire thing. Looking back at this legend, this emperor and this man are speaking, and this man is asking, I only wish for this. Give me 1 grain of rice for the first square of the chessboard, 2 grains for the next square, 4 for the next, 8 for the next, and so on for all 64 squares. So each square has to have double what the square before it has. So here it's asking, well, write the expansion for the amount of rice the inventor of the game of chess received. Well, the man who was asking for that, right? Well, you know, the first for the first square on the chessboard, there's only 1 piece of rice. For the second, there's 2. For the third square, there's 4. And so on. Then there's 8, then 16, then 32, and so on. And you can actually write this in a different way. So the 1 we can leave the same. Then we can say, okay, well, 2 to the first will still give me 2. 2 to the second is actually 4. 2 to the 2 to the third gives me 8. 2 to the fourth gives me 16, and so on. So we can use a power of 2 for every single number except for that very first one, because there's only 1 piece of rice in that first square. So we need to try to see, okay, well, there has to be an easier way for us to do this than having to calculate this for each square 64 times. So it says, okay, well, apply the equation from number 2 right here to the solution you found in part 1. So how many grains of rice did the inventor receive? And it says you can use your calculator to represent the sum. So if I replace x by 2, I can try to solve for this. But here, I just want to explain one thing. The only difference between this equation 1 and this equation 2 is that whenever we're multiplying by x minus 1 to some sort of polynomial, this is the identity that we came up with. However, if we're dividing back by that x minus 1, so we're dividing by x minus 1 on both sides, that's how they get this one. All right? So, now, I need to apply equation 2, they said. So I need to apply x to the n plus 1 minus 1 all over x minus 1. So what I'm going to do is I'm going to put a 2 in for x because I'm going up by double each time and we're using a power of 2. So I'm going to use 2 instead of x, and I'm going to get 2 to the 64th minus 1 over 2 minus 1. And then if I simplify this further, I get 2 to the 64th minus 1, which is equivalent to approximately 1.845 × times 10 to the 19th. So that's a very, 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 very big number. And then it says, okay, well, now I use the same technique to calculate the sum for the following expression. And this time I'm replacing my x with a half. So I'm going to say, okay, well, I have a half, and my n value is 10. So I have 1/2 to the 10 plus 1, subtract 1, all over 1/2 minus 1. So here, if I solve this, use your calculator, the numerator and denominator, make sure you have parentheses around them. If you're hitting the divide button, make sure that they're both separated by parentheses. Order matters when you're dividing. So here, when you're putting this in your calculator, you're going to get something like 1 and 1023 over 1024. So this is going to give you approximately 1.99902, and so on. We get a similar identity if we multiply by x plus 1. So here I distributed everything for you. So we just have to make sure we're simplifying correctly. So negative x squared will cancel, x and negative x. So I'm left with x to the third plus 1. Then over here I distributed already, negative x to the fourth, x to the fourth, x to the third, negative x to the third, negative x to the second, x to the second, x and negative x will all neutralize, and I'm going to be left with x to the fifth plus 1. This last example, we have negative x to the sixth and a positive x to the sixth, x to the fifth, negative x to the fifth. We have negative x to the fourth and x to the fourth. That neutralizes. We're going to keep going here, x to the third and negative x to the third. Then we have negative x to the second and x to the second. And we have x and negative x. And you have to be very careful because right there I just forgot one of my terms. So if you forgot one of your terms, then it would not have worked out the same way, but you would have been left with x to the seventh plus 1. Again, a general algebraic identity for solving this would be x to the n plus 1 plus 1. And then it says use a generalization in number 5 to factor the following binomial. Because of this identity, I know that I'm multiplying by x plus 1, and then I have a leading term of x to the eighth going downward. And notice that my signs are interchanging.